All right. Hello, everybody. I'd like to thank you for, okay. I'd like to thank you for the sincere answers that you put forth onto the question for today. What do you think of what 3 to 5 words what 3 to 5 words do you associate with success? We will be talking about, I did this for one reason. I'm just curious what you think of as success. Part of it was a genuine curiosity. The other part of it was we'll be talking about a statistical method called implicit association tests that utilize this very technique. And it's been growing in prominence in our field. And a few people in this department have been working in political science and politics have been working on it. So we'll talk about that at the end. I was also just a little bit curious as to what you'd say to these answers. So thank you for sharing. Definitely. Okay. Let's do this. Oh, let's close this out. Oh boy, happiness grades win. Okay, I'll leave those be now. But thank you for sharing those. So, full screen, hold on. View, enter full screen, there we go. So today we're going to talk about correlations and working on a Z-scale, both of which are going to be crucial concepts for the rest of the semester. So the correlation, we'll get to that. On administrative matters, problem set 1 is out. So start it if you have not, please. Along those lines, when I said that you can talk to anybody about it, I did literally mean you can talk to anybody about it. That includes McGraw and office hours. The preceptors have been instructed to not give you direct help on your code. Does that make sense? So if you'll notice, the preceptors have been a little bit evasive on this. That's why if you've gone to the office hours, hopefully helpful, but also not hopefully doing it for you, they can direct you towards parts of the handouts and precept where there's similar code. Okay. The second part of that is McGraw. Feel free to use McGraw, but I can't guarantee that they will give you the right answers. So if the preceptor or I give you a wrong answer, you will get credit for it. If McGraw does, you will not. Cool. I don't want to dismiss McGraw. It's actually an essential part of this course. Any mistakes due to us will not hurt your grade. This just came up in the last 45 minutes to an hour, but there might be some issue with the coding of one of the variables. We'll handle it, we'll make an announcement, but if you answer the questions in the problem set as written, you will get an appropriate grade. If you correct some mistake that we made, you will also get an appropriate grade. Our mistakes don't fall on you. Does that make sense? Cool. That's just a general policy in here. Any other questions on the problem set? It's hard copy due in class before next lecture. We'll have boxes. Any other questions with that? Okay. So today we're going to talk about a Z statistic, correlations, and scatter plots. These are all going to come together and give us, we're going to start talking about handling data as actual data, not just representing it as figures. And we're just going to continue along those lines. The first thing to discuss is the idea of mean squared error and root mean squared error. In the statistics literature, these are just abbreviated to MSE and RMSE, and everyone knows what they mean. The mean squared error is a measure of how accurate your prediction is. And we'll be using it as a measure for how accurate an estimate is of some future outcome, or even in the data. It's just an average in how close the data is to our estimate mu. How spread out is the actual data around our estimate. The root mean squared error is just the square root of the mean squared error. And in this case, the root mean squared error is a standard measure of the accuracy of a prediction. What does this mean? The root mean squared error gives an answer to the question, on average, how close is our prediction to the outcome? All right. So it's a standard measure for how accurate your predictions are, or to describe it slightly differently but equivalently, it's the expected or average error in your predictions. Okay. So if you ever end up running a model or commissioning a model or implementing a model that's trying to predict voting or conflict or kinship networks or stock prices or the weather or sports games or whatever, root mean squared error is almost certainly going to be the accuracy measure that you use, because it's an estimate of, on average, how far is your estimate from the actual predicted, how far is your prediction from what you're trying to predict. Okay. We'll be using it as a standard measure in here for those purposes. Where does this come in handy? Political scientists try to predict elections. It's not what we do professionally for most of us. It's something that comes up every 2 or 4 years, and we just have a fun time playing with data and using all the things we're going to teach you and going like, here's who's going to win. This game's been around for a while. It began in the mid-70s, but this comes from a classic paper in 1989. And I just liked the title of it. Why are American presidential election campaign polls so variable when votes are so predictable? And this paper just began with the following empirical puzzle. And the paper dates back to 1989 or 90. But it turns out that if you tell someone a year before the election how the economy's going, whether we're at war, how long that incumbent president's party has been in office, what's happening to unemployment, what's happening to GDP, and inflation. If you give someone those 5 pieces of information, we can actually predict the presidential outcome really, really closely a year out. Okay? Those sort of systematic or structural factors are really, really useful at predicting presidential outcomes. What's not useful at predicting presidential outcomes a year out are polls. It turns out 6 months to a year before an election, the relationship between presidential polls and what actually happens is nil. So this paper sort of brought a bunch of ideas together, but started to just ask the question, why, if I give you all these structural factors, can you tell me what's going to happen in the presidential election a year out? But if you ask people who are actually going to vote in a year, they don't know. The short answer, and it shows up, the short answer is it shows up right around here and takes off, is the American public kind of doesn't pay attention, at writ large, doesn't pay attention to presidential elections until the conventions, which is right around Labor Day. So before Labor Day, people are busy living their lives. And then after Labor Day, people tune in at one convention, then the other convention, then maybe a week before and make up their minds. And that's when most voters make up their minds. But what they used to make up their minds are their structural assessments of how the economy is doing, and then some other things about the candidates themselves. And this paper sort of highlighted all of that. The question that shows up, though, coming back to root mean squared error, is how accurate are polls before the election? So the previous data was from the 1988 election, which was George H.W. Bush and Walter Mondale, I believe. No, Dukakis. Thank you. And in that case, we saw that people started to pay attention about 30, 40 days out. This figure is updated for 2018, looking at the root mean squared error of polls as a function of how far we are from the election. Okay. So in this case, if you're looking at a senatorial poll, the error about 90 days out is about 4%. And day of, the error is about 2.5 percentage points. So that means, and we're just looking at senatorial polls, we'll do this same game for a moment with the other ones, is that if you're using polls to predict a senatorial race 90 days before an election, then we expect there to be a 4-point difference between how the senator actually does, how the candidate actually does, and what the poll says. In any sort of close race, the polls are just not useful, right? Like being within 4 percentage points is a lot in most races. So that's going to tell you that a Democrat's going to take California and a Republican's going to take Utah, but like we didn't need polls for that. All right. The last part is a little more subtle and important, which is that day of, we expect the expected error in a poll, day of in a senatorial race is 2.5 percentage points. So what that means is if you're less than 2 percentage points of the truth, if your poll's within 2 percentage points of the truth day of the election, you're doing well. If you're within 1 point, you're doing well. And this is part of an argument that polls are not wildly useful in close elections. Right? In the last presidential election in this country, was there any poll that could have predicted the Georgia Senate race? No, it came down to a couple hundred people. Arizona the same way as well. So the takeaway here from this, and if you look at these, and this isn't a presidential race. This would have been the 2016 race. The expected polling error was about 2 percentage points, which means that if you look at data and you get a certain standard error or a margin of error confidence interval around the points in its survey data, the best practice is just to add 2 percentage points above, to add 1 percentage point above and below to get that extra 2% width. And for folks who follow these things with betting markets or sports markets, 538, we'll talk about 538 down the line. And the New York Times all have different statistical methods for predicting these races. It's increasingly common to just tack on this error at the end because we know it's there. This is technically referred to as irreducible error because even if you take a poll the same day as the election, you're going to be off by 2 points on average. All right. What does this, what concept are we using from the course? The standard measure of all these things is root mean squared error. They take, for each of the elections, they take the polls day of and the election outcome, take the difference, square it, average, square it, average, square root. They literally follow this equation here. It's a standard measure for predictive accuracy. Another concept we'll be using in here closely related is the standard deviation. And it's closely related to the root mean squared error, but we're going to make good use of the standard, okay, that's a judgment call. We're going to make a lot of use of the standard deviation here in this course. The standard deviation answers the following question. On average, how much does a data fluctuate around its sample mean? Okay. So it's the root mean squared error, but applied to the sample average. The z-score is the following. The z-score is a data point minus its mean divided by the standard deviation. To put it differently, the z-score answers the following question. How many standard deviations is a point from its mean? All right. Why do we do this? Most of the work that we're going to do in here mathematically actually takes place on a z-scale at some point, because a z-scale is referred to as a scale-free distribution. If you take an exam in a class and you come back and you say, I was 3 standard deviations above the mean, right? Does that tell you anything about what grade you actually, does it tell you anything about what score you actually got? Or how many points the exam was out of? Or what your actual grade was? No. It just says that relative to the mean, you're 3 standard deviations out. So what you can do is you can actually take that sort of comparison and use it across classes. If you're 2 standard deviations above the mean in all your classes, we say you're doing well relative to everybody else, but we never actually reveal what your score is on the exams. Z-statistics are the same way. Z-statistics function as scale-free statistics in the sense that they take a statistical question and they strip out the underlying measure. So let's see, I think that's, so what the Z-statistic does is if I have data that's measured in miles and data that's measured in kilometers and data that's measured in dollars and data that's measured in survey responses, each one of those, when I put them on a z-scale, they come down to the same scale and I can compare them across variables, regardless of the underlying measurement, which means that I can have a unified statistical theory that's independent of how I happen to measure a variable. That's what the z-statistic is going to give us. We'll talk about how this can be used in a normal approximation in a little bit, but it's how far the point is in standard deviations from the mean. The next idea we're going to flip to is the correlation statistic. The correlation statistic is closely related to the sample covariance and standard deviations, but before we go into the mathematics and the equations of it all, I just want to give an idea of what correlations mean when you plot data. So what I include here are different data sets where the correlation is -1. Correlations, let me back up for a second. Correlations run from +1 to -1. They can't be larger than 1, they can't be smaller than -1. If two variables correlate perfectly, then they fall on a straight line, like so. If two variables correlate negatively perfectly, then they fall on this straight line, okay? So if two variables are perfectly collinear, then they correlate at either +1 or -1. If I were to measure everybody's height in this room in inches and then centimeters, the correlation of those two measurements would in fact be 1. If I were to measure how far you are from the ceiling and how far you are from the floor, how far your eyes are right now from the ceiling and how far they are from the floor, that would correlate exactly at -1. All right. What I want with this particular slide, and feel free to reference it in the future, is to give an idea of what we think of as a relationship in the social sciences. Okay, so in this case, if you ever see data in the social sciences that just perfectly falls from something else, then you have a coding error. We do not have in the social sciences anything like the ideal gas law, or if I were to regress log energy on the speed of light and log mass, right? Like it would just be perfectly, because E = mc squared would be perfectly linear. We don't have that in the social sciences. I heard a story of some economists who were studying Latin American balance of payments issues. This would have been back in the 80s. And they went through and they thought they discovered, so they went through and they gathered these different measures of budgetary measures from different countries. And they found a perfect correlation, like literally perfect. They thought they discovered some iron law of macroeconomics when in fact the countries were all using this other variable to create that one. Okay. If you get a correlation between two variables of 1 or just really close to 1, then the relationship is deterministic, and nothing in our world is deterministic here in the social sciences, at least. If you're talking about engines and rocket ships and stuff, then you want it to be perfect. But we're talking about voting. We're talking about when you make friends. We're talking about different types of discrimination. We're talking about conflict. We're talking about ethnic groups. We're talking about public opinion. All of that has a strong random component. So back to this figure, if you see a correlation of -0.75 or +0.75 and the data kind of looks like this, you found a strong effect. That's just what we think of as a really, really strong effect. Okay. There's an interesting sub-literature in economics pointing out the fact that the social sciences have pretty much found all the strong effects that are out there. The reason for that, we know that our countries that are next to each other tend to go to war more than countries that aren't. We know that Democrats vote for Democrats and Republicans vote for Republicans. Like we know that increasing public sanitation decreases mortality across the board by a lot. Like we know all the big effects out there. So these -0.75 and 0.75s are out there, but they've probably already been discovered for the most part. Normally, if you look at this -0.5, it's starting to look more like a cloud, right? Most of the research that lives in this -0.5 or this -0.25 range. So, and the reason I'm doing this is I just want to communicate this point. When we say we found a strong, significant effect in the data, for the most part, we're saying that the curve looks like this or looks like that. It's around the ±0.25 range where most of our work is done. So even then the effect is discernible when you look at the data, it might not be strikingly obvious to the eye. And then this is a correlation of 0. Can folks distinguish the correlation of 0, which means there's no linear relationship, Can folks distinguish the correlation of 0 from the plus or minus 0.25? It's kind of tough, isn't it? Generally, being up here is nice when you look at the data, because then I think the 0.5 is distinguishable to the eye. Okay. So the correlation statistic measures the relationship between two variables, and let's just talk for a moment about how it's constructed. The correlation statistic is the sample covariance, but it's scaled to range between plus or minus 1. The nice thing about that is that if I give you any two variables, you can tell me what their correlation is. And it will always fall between plus or minus 1, which means correlations are comparable. That's what I meant by scale free. They're comparable in the sense that if two variables have a correlation of 0.8 and another have a correlation of 0.6, the 0.8 has a higher correlation, regardless of how we measured those variables. So to talk about how the correlation is constructed, it's actually the covariance divided by the product of the standard deviations. If you, and this is confined to run between plus or minus 1. If folks, has anyone heard of the Cauchy-Schwarz inequality? Any hands, couple hands? Okay, that this is bounded between plus or minus 1. Yes, I know grad students. That this is bounded between plus or minus 1 is a direct consequence of the Cauchy-Schwarz inequality. Another way to think, so one way to think about the correlation statistic is it's the covariance divided by the product of the standard deviations. Another way to think about it, though, is that it's the covariance on a z-scale. So if you take the numbers and put them on a z-scale and calculate the covariance of those numbers, then you get the correlation statistic. Both are equivalent ways to think about it. This question came up, so I just want to clear the air with it. Do I need to know this for the exam? It's a fair question. Grades are a part of this course, right? It would be good practice, especially if it's mentioned in the paper, just to write these equations down. I'm not going to ask you to reproduce them. I'm not going to give you 10 numbers by hand and have you calculate this out. What I will ask you to do is know that the correlation runs between plus or minus 1 and has the same sign as the covariance. So if two variables have a positive covariance, they have a positive correlation. If they have a negative covariance, they have a negative correlation. And I'm going to need you to be able to handle it qualitatively in that regards, but I'm not going to give you X's and Y's and ask you to chug through that with a handheld calculator for me. All right. Okay. So if you'll notice, in constructing the correlation, we divide by the means of the two variables and subtract off and divide. We subtract off the means and divide by the standard errors. We subtract off the means just to center both variables on their sample mean. This means if we were to move the measurements from Kelvin to centigrade, we'd get the same correlation. Why divide by standard deviations? Well, this way, if we were measuring in inches versus feet, we'd get the exact same answers. We don't want a correlation statistic that varies based off whether the researcher decides to measure something in kilograms instead of pounds, or dollars instead of euros, or so forth and so on, right? We want our statistical inference to be not even robust, but irrespective or independent of those measurement choices made by researchers. Working in a scale-free distribution with a z statistic or a correlation accomplishes that. One question that we'll refer to a little bit later in the course, but to give you an idea now, is when is a correlation distinguishable from noise? These are rough cutoffs for now. We'll go into the specifics of this a little bit later. But if you have 20 observations, then you need to have a correlation of above plus or minus 0.45 to say the effect is systematic or likely not noise. If there's a correlation, if n is 50, that number drops to 0.28, then the cutoffs are here. For n of 1,000, so if you have 1,000 observations on two variables, if the correlation is above 0.06 or below negative 0.06, then we can say that the effect is likely, the correlation is likely not noise. All right. That's just something to grasp onto for now. One warning that's worth noting with correlation statistics is they measure linear relationships between data. So this data right here is known as Anscombe's quartet. Anscombe was a famous statistician. And in each of these data sets, the correlation between X and Y is 0.81. But what you'll notice is that for each of these, they have the exact same correlation statistic. And what I presented as correlations on the previous slide, you might look at and think of something like this, right? But if the data looks like this, which is clearly there's clearly some nonlinear relationship, the linear correlation is exactly the same. This correlation happens to be exactly 1, except for that one observation. This one observation is dropping the correlation down from 1 to 0.81. And then this correlation here happens to be exactly 0, except for that 1 point. The takeaway from this figure up here is there might be nonlinear relationships in your data that the correlation is missing. That's why we spent the first part of the course talking about plotting your data and look at it. Always plot your data and look at it. This line is telling us the correlation might actually be really high except for one datum. Plot your data and look at it. This one is saying the correlation might actually be 0 except for one datum. Plot your data and look at it. So each of these are cases where if you might think something like this is happening, but any one of these could be happening instead. Again, just scatter plots. We'll talk about how to do that. Trying to gauge where this falls on the chuckle meter. It's not a belly laugh. Did it rise above smirk for anybody? Was it below smirk for anybody? Did it at least hit smirk? Okay. There's a comic called XKCD, which has replaced the Far Side on doors of physicists over the last maybe 20, 30 years. And for a while in this course, I'd actually choose an XKCD comic in the quiz and say, why is this funny? And that was just a standing question on every quiz. So for years, the students here were going back through XKCD for the last 3 months, trying to find anything to do with statistics and why it's funny. We'll have a few more XKCDs pop up. All right. So correlation is not causation. I hope people have heard that at some point. That doesn't mean we shouldn't talk about causation. That doesn't mean we should dismiss correlation. It just means we shouldn't do so thoughtlessly. So there's listed here 4 different ways that an observed systematic correlation may not be causal. The first one is confounding. We may think that a correlation between 2 variables means that one is causing the other, but there could be a third variable driving both. It could happen. The second is endogeneity or reverse causation, where if there's a strong correlation between 2 variables, we think variable A might be driving variable B, but actually variable B is driving variable A. These sorts of discussions actually have profound impact on policy, and we'll talk about these sorts of questions down the line. We have a few data sets to go through with this. Another one is misspecification. We talked about the ecological fallacy. You might be mistaking within group behavior for a cross group behavior. We'll have another example with that one. The fourth one is the one I want to dwell on for the moment, which is simply that the correlation may appear large by chance. The world is a big, beautiful, mysterious, scary place. And there's lots of things correlating, and a lot of them look like they're correlating at really high levels. That doesn't necessarily mean that there's a relationship between them. This is driving home the idea that you should have a mechanism whenever you do social science work, and your thoughts on the mechanism should precede the data. Okay, we'll return to that, but we're going to talk about spurious correlations. Spurious correlations are variables that correlate really, really highly, for which it's probably safe to say that there's no causal relationship between these 2 variables. To give you an idea, there's a correlation of 0.66 for over time from 1999 to 2009 of the number of people who drowned by falling in a pool and the number of films Nicolas Cage appeared in. Now, one question, what is the best Nicolas Cage film or the worst? And I realize those might be the same film. National Treasure, is that what we're going with in here? Any other ones? Really? I have not seen that. Are any of them really good by any chance? National Treasure? Okay, Raising Arizona if you're in a mood. But does anyone think there's a causal relationship between people watching Nicolas Cage films and then jumping into pools? No, these just, okay, so at least we should do a follow-up study to be sure that's not the case. But sometimes these can be humorous, things just correlate in weird ways. It turns out that the divorce rate in Maine correlates with the per capita consumption of margarine at 0.99. Why is that? Because eating too much margarine leads to unhappy marriage. No, that's not why at all. These are just examples of things that correlate in weird ways. Unfortunately for the next one, all of the preceptors this year, normally we have a sociologist or two. Is this the next one? Yes, they're all from political science, but if you guys want to switch over after this, let me know. Worldwide non-commercial space launches, especially we can explore this, especially with what's his name doing what he's been doing, SpaceX, Elon Musk. The worldwide non-commercial space launches correlates with the sociology doctorates awarded rather highly. I don't know what they're doing in the sociology department, but it looks like they're having more fun than me. Another one, letters in the winning word of Scripps National Spelling Bee and numbers of people killed by venomous spiders. I don't know if there's any spelling bee champs in the room who could shed any light onto that. Another spurious correlation, oil, Islam, and women, published in our top political science journal. In this case, you've seen this data, the Islam and oil data, you've been exposed to that in your handouts, right? Okay. Sometimes the lectures are a little off based off whether the first lecture is the first week or the second, you know, if there's a one lecture first week or second, but you have seen this data. The author in that study was arguing that there's a relationship between female labor force participation and level of oil in a country, right? And in actuality, we took that data and we just partitioned it into two groups. Countries that are red are in the Mideast. Countries that are red are in the Mideast. Countries that are blue are not in the Mideast. Countries that have solid dots are high Muslim countries. Countries that have open dots are low Muslim countries. By low and high Muslim, I just mean that there's a high and low proportion of Muslims in the country. One of the things whenever I say things like that is if you're raising your hand going, there's radical differences between different sects of Islam. Please raise your hand and yell those things at studies that do this sort of work. Okay, differentiating Sunni and Shia is very important when we talk about Islamic countries. Differentiating South Asian countries from African countries from Middle Eastern countries is hugely important. There's some real heterogeneity that we need to get. The original paper did not, but what you'll notice is if none of this data were colored, you'd actually see a particularly strong relationship over all the data. But looking at it, what you find is that there are countries in the Mideast that happen to have a large number of Muslims in it that are driving the entire effect. So all of the the correlation between oil rents per capita and female labor force participation, the entire story that the author was telling was centered on Middle Eastern countries with a large proportion of Muslim residents. And that's a good and important story to tell, but he never acknowledged the scope conditions of his theory. Scope conditions meaning where the theory applies and where it doesn't. He was arguing broadly that it was oil, not Islam, that was driving labor force participation, when in fact, from his own data, this story appears to be much more contingent. Okay. Let's see. Anything left with this? No, but we might bounce back to that example. Oh, one thing to point out with this example is that the y-axis is converted to a z-scale. And I think you saw that in the data. That's why it was coded Z Islam in the data set. Recoding your variables to a Z scale is something you'll almost never have to justify. If you do it, nobody will ask why you did it. They'll just assume you did it for a good reason. Okay, that's not a choice you have to defend. All right. The last thing to talk about correlations. We have a few slides coming, and we're going to talk about a recent method called, well, it's a really old method that's been reused in brought back into political science, I think for good reason recently. And it shows up every now and then. But the idea we're going to talk about are word association tests. And the idea itself actually goes back to Carl Jung, the psychologist, who was arguing that our brains have these interconnected web of ideas. And one way to get at what these ideas are talking about are by prompting you with words and asking your responses, which is what we did at the beginning of class with the question about success. You just did a word association test for me on that question. Now, this paper came from, I think, a particularly trenchant critique of most public opinion surveys. And the authors are all interested in studying public opinion in China. So in this case, the questions you get are something along the lines, this comes from a study that some friends of mine did, on a scale of 1 to 10, with 10 meaning very satisfied and 1 meaning not satisfied at all, how satisfied are you with the work of the following? Central government officials. So there's two different problems that these sorts of questions pose. The first is that people might not be entirely honest about their thoughts towards the central government or the president of China in China. There's a fascinating debate in Russian politics where if you ask polls on what Putin's proper popularity is, what is, Jacob, it clocks in around what, 80%?
Right now it's at about 51.
What is it at?
61.
61. Okay. But does anyone trust that number? There's lots of reasons to distrust it. People aren't always forthright with these questions, and it's not clear what's meant by public opinion. The second issue here is, the second issue in this data, though, or the critique these authors argue, is that mapping things to a 1 to 10 scale sort of skips past how people construct approval in their heads. Does that make sense? So you have this multi-dimensional conception of central government officials, and by being forced to map it back to a 1 to 10 scale, you're brutalizing the response in some regards. It's helpful because this 1 to 10 scale can then be compared across individuals, but you're losing some of the subtlety and nuance of the underlying opinion by forcing it down into this one dimension. So an example the authors give of a mental map is results that come from just prompting people about Barack Obama. So if you just say Obama, and this comes from an earlier study that used this, if you just give people the word Obama and ask them to give their 3 to 5 words, like I did with you, here's what you get. Smart correlates positively, healthcare reform correlates positively, war in Iraq, immigration has a negative valence to it, oil spill has a negative valence, African Americans is positive, Jeremiah Wright is negative. But what you'll see is you sort of get a mapping out of all the different ideas connected to the former president. The idea here is that instead of measuring public opinion, we need to sort of measure these mental schemas that people have in their heads for how they conceptualize, because when you say something like Barack Obama, Donald Trump, Joe Biden, I'm going to stick with the American example because just for now, when you say things about that, it doesn't trigger just one dimension, it triggers an entire flood of ideas. And we want to capture how those ideas are organized in people's heads. So the word association test is one way to do that. You prompt people, you measure the 3 words, and then you calculate the correlations between the words and the prompt. But then you also calculate the correlation between the words and each other. So in Obama's case, if people are likely to say healthcare, well here, people who are likely to say African American when prompted by Obama are also likely to include the word Jeremiah Wright. Those two sort of cluster together or are co-occur or are co-mentioned. Any other branches, vote Democrat, liberal, and Democrat all correlate, whereas angry Wall Street bailout, Democrat all correlate as clusters. And what it does is it pulls out, you can use correlations to pull out these clusters of co-occurring words. And all this is done by measuring the correlation between how frequently these words are mentioned. Let's see. The particular study under discussion for the implicit association test, the authors prompted 3 different questions in their study. The keywords they used were central government, CCP, the Communist Party, and then China. And they did the exact same thing with respondents that I did with you with success. What are the 3 words, 3 to 5 words that you use and associate with this? Okay. So the first order concern or the first order measurement is which word gets mentioned the most. So in this case, this is the probability, this is the frequency that a word shows up, and then this is the frequencies on a density scale. So this is the probability, if someone says central government, this is the probability that the word government shows up, given they were cued with central government, about 8% of the time. So if I say central government and you say government, right, that's a natural thing to reply. The other common reply is country, leadership, authority, CCP. So these are the words that, given someone says central government, this is what you're going to say. Similarly, if someone prompts central Chinese, CCP is Chinese Communist Party, right? I thought so. Okay. So in this case, for CCP, it returns China as the most commonly returned word. Leadership, people, great, party member, CCP, okay, thank you. Ruling party, and all seem like they have a certain type of validity called face validity. Face validity means you just look at it and you're like, yeah, that makes sense, right? I mean, then if there's China, powerful, motherland, great, country, China, let's go, and people. So what we're seeing in here, and just to highlight one of the things, this over here, this column is a probability, which means it's going to add up to 1 if you add up all the way down the chart. And what that allows you to do is, even though these frequencies are different, 76, 89, and 177, you can put them on the same scale by putting them on a density scale. And you can compare the relative frequencies in each of these. So the most common, the strongest answer is right here. Okay. This is a co-occurrence network. So what the authors did was they took all their answers and they turned it into a correlation matrix. And what the correlation matrix is it's just a matrix with the number of variables in rows and the number of variables in columns. And every entry in the matrix is just the correlation between how often two words occur. So they took this matrix with number of rows, number of columns, and then just measured the correlation between how often 2 words occur. And this is the mental map they constructed to the CCP response. So what comes out in here? Here's CCP. Money. Okay. Chairman Mao and Deng Xiaoping come in close, near here. Leader, red, government, country, China, national flag, motherland, ordinary. And what this figure is doing, in some regards, is it's capturing the co-occurrence of words that are initiated, triggered, or associated with CCP. So when someone says, what is your opinion of the CCP on a 1 to 10 scale? And they return a certain number, they're taking a figure like this in their head and mapping it down to a 1 to 10 scale. The advantage of the 1 to 10 scale is that we can put that in a statistical model. The disadvantage of it is you're losing all of the subtleties of the underlying concepts and how they map down to that underlying scale. All right. But all of this is literally being done by examining the correlation between when words co-occur. Oh, how do words differ between, they did the experiment, they did this survey in the mainland, and then they also did it in Hong Kong. And for the keyword democracy, you might want to know, or the authors wanted to know, which words are more likely to show up or be associated with democracy in China versus Hong Kong. And in China, the word democracy was more likely to be associated with equality, harmony, people. And that's what people would respond in China relative to Hong Kong. Whereas if we look at the Hong Kong words, democracy, freedom, US, no, and Taiwan show up as the words most associated when prompted by democracy in Hong Kong itself. So even though we're not able to get these 1 to 10 scales of public opinion, we are able to get measures of individual words that can convey useful descriptive statistics about the underlying public opinion. The disadvantage of this method is when we run a linear regression, you can't turn this into a variable very easily and put it in a model like you can with a bunch of 7s and 3s and 5s and 4s. But the subtlety of the information that you get out, I think, is worth it. Okay, I want to point this out because we'll talk in here a few different times. This is the first case we're talking about. We talk about surveys quite a bit where you call people up, or you don't use phones anymore. Whatever you use to talk to other people. You find them and you ask them questions, then you just grab the data and average it. This is a more subtle measure of what you're trying to get at than simply asking, do you approve of this or that or the other thing? Okay, so I just want to highlight this as a potential methodology that people might be interested in. In the last moment, there was a whole thing about reunions. No one's been to reunions yet in this room, just definitionally, right? You have been? Awesome. Alumnus or?
I worked it.
Oh, you worked it. How was it? It's like a big orange themed wedding. I don't know how else to explain it. Crowds grow exponentially. And the only point of this last slide is that you should take logarithms because it takes data that looks like this and has a distribution like this and makes it normally distributed. Okay. We have about 15 seconds left, so I will just see you on Thursday.